Hello everyone, my name is Gabrielle Kowkabany and I'm a junior chemical engineering major studying under the direction of Dr. Yuping Bao in the Nanobiointerface Laboratory, working on a project entitled Structural Effects of Various Flavonoids on Ligand-Iron Complex Nanoparticle Formation and Their Applications in Drug-Resistant Cancer. Although breast cancer treatments have improved tremendously in recent years, chemotherapy is still the mainstay treatment. These are three of the most common chemotherapies, paclitaxel, cisplatin, and doxorubicin, that are used on breast cancer today. However, these chemotherapies cause a lot of major side effects, including nausea, vomiting, and weight loss, as well as drug resistance development in cancer patients. And so there is a huge need to come up with ways to mitigate side effects and drug resistance because of these common chemotherapies. And so there has been a lot of focus in recent years on the use of natural products. Specifically in my lab, we work with flavonoids, which are natural plant pigments that have anti-cancer and antioxidant effects. Currently, there are over 6,000 known flavonoids today, which all have a very similar structure, which you can see in part A of the figure, this polyphenolic compound. But unfortunately, these have very limited pharmacological applications currently because of their low aqueous solubility and their poor overall stability. So previously in my lab, we have worked with quercetin, which is one of these flavonoids, in order to try to overcome these limitations. In order to do this, we have taken quercetin and used iron to form a metal complex, and then used excess iron to form a nanoparticle. And in preliminary cellular findings, we showed that this improved bioavailability of quercetin, enhanced its anticancer and antioxidant effects, blocked ABC transporters, which is a key mechanism of drug resistance, and these nanoparticles were found to be minimally cytotoxic. So with my research, because there are over 6,000 of these flavonoids that are known to exist, I'm trying to see if this synthesis process can be replicated and how these structural differences of these various flavonoids will affect this synthesis. Second, I want to understand if the properties of these flavonoids are altered in any way when the synthesis is complete. And finally, if these nanoparticles have applications in drug-resistant cancer. In order to study these things, I am primarily working with three flavonoids, including quercetin, luteolin, and naringenin. Now, I know it looks like I have the same image of each of these flavonoids up there, but I do promise that they do have some key differences, which I'll highlight. All of these have an acetyl group. However, quercetin and luteolin have a catechol group, these two hydroxy groups at the top, whereas naringenin does not. It only has one hydroxy group. In addition, quercetin has a maltol group, but luteolin and naringenin are missing this hydroxy in the middle ring structure. And finally, naringenin is even more different from quercetin and luteolin because it doesn't have a double bond in the middle ring. And so in light of these structural differences, I wanted to understand the pH-dependent stability of these flavonoid structures. And so I did this with luteolin and naringenin by putting them in solution with no pH adjustment, a pH of 5, a pH of 7, and a pH of 9, and looked at their UV-vis absorption spectra in addition to their Fourier transform infrared spectra. And what I found for luteolin is that it has two distinct absorption bands at 254 and 348, which is consistent with literature values. But when the pH was increased to 5, there was a slight shift in this absorption, which indicates possible deprotonation. But then at a pH of 7 and pH of 9, there were further shifts which indicate the formation of degradation products. And this was confirmed with the FTIR spectra that I ran. And so at 3,400 wave numbers, there was a broadening that occurred, and additionally, from the 1600 range to the 1700 range, there were additional peaks that indicate the formation of carboxylic acid groups, which are found in degradation products of luteolin. When I did this for naringenin, I found that there was actually only one absorbance band recorded at around 289 nanometers, and this is also consistent with current literature. And that was the same for no pH change, and then also at pH 5 and pH 7. However, at a pH of 9, there was a clear degradation product formed, which was confirmed with FTIR. So moving forward and thinking about synthesis, because luteolin was not very stable at a neutral pH, we actually did not use it in our synthesis of nanoparticles because it doesn't have a good application in cellular studies. However, naringenin did. And so in order to synthesize these nanoparticles, a 10 millimolar naringenin solution was dissolved in ethanol. And then iron chloride was added to it in order to form complexes, which was noted by an immediate brown or blackish color change. And at that point, I checked the pH of the solution and then adjusted the pH using ammonium hydroxide because it was quite acidic, which caused it to change kind of an orangish reddish color and then allowed it to stir for 2 hours. In order to characterize these nanoparticles, I used transition electron microscopy in order to visualize the size and morphology of the nanoparticles. I used UV-vis spectroscopy and FTIR as well. So this is the characterization of my nanoparticles using naringenin. And so in part A of this figure, you can see the TEM image taken. And so this is for a 1:5 naringenin to iron ratio of nanoparticles, and you can see that these are the black dots that are in this image. They're around 10 to 20 nanometers in length. And then I confirmed with FTIR spectra that iron coordination did actually occur. And so these are really nanoparticles that you're seeing. And so you can see in part C of this figure, at the 1400 range, there's a big peak in the red line where that's the nanoparticle. And so that is demonstrating that there's iron coordination around the ketone group of naringenin. And then the peak around 435 is iron coordination with the hydroxy group at the top of the third ring in naringenin. However, the UV-vis absorption spectra actually didn't really demonstrate that anything happened at all, which was quite curious to me because when we did this with quercetin, there was a clear shift in the peak, but you can see that the peak is around 289, 290 like it was for naringenin by itself. And I hypothesized that the reason that this is this way is because naringenin lacks that double bond in its middle ring structure, and so therefore when iron chelation occurred, there was actually no electron transfer happening. That resulted in a shift in the UV-vis absorption spectra, which is why it's still around that 290 peak. So in conclusion, I was able to successfully synthesize naringenin iron complex nanoparticles with multiple ligand-to-iron ratios. And I also found that the synthesis of luteolin iron complex nanoparticles are highly dependent on pH. However, because luteolin is very stable in highly acidic conditions, it may actually have applications as an oral route because it can survive stomach acid. So we may look into further applications in that way as opposed to cellular studies. In the future, I plan to conduct a thermogravimetric analysis, or TGA, and isothermal titration calorimetry in order to confirm the proposed iron coordination sites that were observed in the FTIR spectra. Additionally, I plan to complete a DPPH assay in order to study the antioxidant effects of the naringenin iron complex nanoparticles compared to free naringenin to assure that its antioxidant properties are maintained even in nanoparticle form. Finally, I plan to utilize these naringenin iron complex nanoparticles in cellular studies to determine their potential role in overcoming drug-resistant cancer. Thank you so much for listening, and I am now open to any questions you have.
So do the flavonoids you're studying have any useful applications other than cancer?
That's a great question. The answer is yes. These flavonoids have antioxidant and anti-inflammatory properties, and so they especially have applications in the realm of aging-related diseases. So things like Alzheimer's and other neurodegenerative diseases, and specifically for naringenin, that's a very common application. And so there's actually a collaboration in my lab that we're doing looking at if these naringenin nanoparticles can actually overcome damage that's done by ischemic stroke, for example.
So I'm curious if there is a particular nanoparticle size that you are trying to achieve, and if so, about what size are you looking for and why specifically that size?
That's an interesting question. The short answer is no, we're not actually looking for a specific nanoparticle size. When we do this synthesis process, we generally study the ratio effects, and so we use ratios of ligand to iron from 1 to 5 all the way to 5 to 1, and then we look at TEM images of all of those nanoparticles to kind of see what size has been created based on the amount of monomer that's available during nucleation and the formation of these nanoparticles. And then from there, we can see the ones that are like most consistently formed. And then generally, if a nanoparticle is around the size of 20 nanometers, that's ideal when you're thinking about the incorporation of these nanoparticles in, for example, a murine model or in human studies, because those won't actually get trapped in organs like the liver or lungs, and they have the highest bioavailability. But really, there's not a size that we're necessarily aiming for. And then to kind of go further than that, if you look back in this image of the TEM, you can kind of see that there's a difference in the uniformity of the nanoparticles that are in this image. And so they're kind of arranged between 5 nanometers to 20 nanometers. And so we're really looking for something that's more consistent than that. And so we can play around kind of with the reaction kinetics and other factors to try to increase uniformity, for example, by doing this reaction at a lower temperature.
How do you know that the flavonoids are not being structurally altered when the nanoparticles are synthesized?
So in order to verify that, first of all, when we're actually adding the iron, chelation occurs with the oxygen and generally like a hydroxy group. So pretty much all you're losing is a hydrogen, and the rest of the structure is staying the same. But we can use the characterization techniques that I mentioned earlier, including UV-Vis and also FTIR, in order to see that the structures are actually staying the same. And then further than that, when I talked about my next steps in looking at a DPPH assay, that will allow us to see if the antioxidant behavior that the flavonoid naturally has is sustained when it's in nanoparticle form. And so if that is, then we know that the structure of the flavonoid hasn't actually been altered.